Namaste. Welcome to this channel, Dr.ARM's Chemistry. We were discussing this theory of acids and bases, in which we have discussed the major point of this topic, that is strength of acids and bases, under this title theory of acids and bases, in which under this point we have discussed several factors affecting the strength of the acids and bases. Now we are going to see this steric effect on the strength of acids and bases. So here we should understand that what is steric effect. When the two molecules of larger size are coming closer, they interfere with each other, means their groups of the molecule repel each other. That is called a steric effect. So this repulsion, if experienced during the process of reaction or during the reaction between an acid and a base, then we say it is steric effect. When the acid-base behavior is observed, the steric influence is also highly observed, or it is highly effective. The reaction may be slower or faster depending upon the steric effect. Means the reaction may be slower or faster when the molecules of acid and base are larger with respect to each other, and during this the bulky groups repel each other, so they develop certain strain which slows down the reaction. When such bulky groups are forced to come together during the formation of an adduct, that is addition product, what happens? The mutual repulsion between these bulky groups repel the molecules away from each other and prevent them from undergoing a chemical reaction. The scientist Brown has worked a lot on this factor, and according to him, means he says that the molecule has the front strain or back strain, and depending on this front strain, that is F strain, and back strain means B strain. So depending upon this, the reaction may be slowed down or affected. The rate of reaction is affected. So depending upon the bulkiness of these groups, it is possible that when we consider acid molecule is bulky, base molecule is also bulky, when the two molecules are coming closer during the formation of an adduct, the two bulky groups or two larger groups which are attached to certain central atom of the element, then they show strong repulsion, as a result of which they are moving away. They are not capable to come closer and form the adduct. So this situation is possible when both molecules of reacting substances, that is acids and bases, are bulky. Then they experience steric strain. Similarly, it is also possible that when the molecules of the same type are bulky, then their bulky groups are also repelling each other. They are showing strain, and this is also resulting in the slowing down the rate of reaction. So in this case, the valence shell electron pair repulsion is observed. Again, if we see that when the molecules of the same type, say acid or base, are experiencing the strain due to the steric effect, then it is called internal strain, and this is observed in many of the molecules. Now if we see the general reaction of acid and base, then we find that say acid is A, base is B, it gives an AB as the product. This gives AB as an product. So the steric effect is pronounced when the bulky groups are there on the base or acid. And if we consider, say, acid is H plus, when we consider here acid is H plus and base is the substituted amines of pyridine, then we can find the order of the basic strength as follows. So here, with relation to this H plus, that is acid, the order of the strength of the basic basic substances, that is strength of the bases, is like this. This is 2,6-dimethylpyridine. This is stronger base than this is 2-methylpyridine. Then this is stronger than this is tertiary, 2-tertiary butylpyridine, and this is NH. So the order of the basic strength of the base is like this. So this is when the acid is smaller, like H plus. But when we take acid, it's larger. When the acid is larger, then like we can consider BF3 or BMe3 trimethylboron. Then the order is reversed because these molecules are more large than the hydrogen ion, that is H plus. So the order is found to be reversed and it becomes like this. Pyridine. So here in this case pyridine, because this is less bulky, means smaller in size. So the order is reversed like this. Then there is 2-methylpyridine. Then the next is 2,6-dimethylpyridine. 2,6-dimethylpyridine. And next is 2-tertiary butylpyridine. So this is the order which is reverse compared to the previous one. Since the acid groups, so these are the acids. So these acids are larger in size. Acids are larger. And therefore, when they want to form adducts, they will prefer to combine with less sterically interfering bases. So the less sterically interfering base is pyridine. Then next to that is 2-methylpyridine. Then next to this is 2,6-dimethylpyridine. And the last is 2-tertiary butylpyridine. So here this 2-tertiary butylpyridine counterbalances its steric effect with the inductive effect because there is alkyl groups. So they have steric effect as well as they are having inductive effect, and that is why the counterbalancing is taking place in this case due to the steric effect and inductive effect. Now here we will also see that the larger species like iodine, here we are finding that these are also fluorine larger, but still compared to fluorine, iodine is larger. Again, there are other groups which are also larger in size. So if the groups are present at 2, that is ortho position, then they are having more interfering effects. So 2-methyl-pyridine is having less basic strength compared to pyridine only, because at ortho position, that 2-methyl, this methyl group at ortho position shows stronger steric effect. Here we find that in this case, fluorine is electron attracting group, whereas this methyl group is electron donating. So because of this, the BF3 is stronger base, a stronger acid. So this is stronger Lewis acid, whereas this Me3 is weaker Lewis acid. So this is because of the difference. Fluorine is electron attracting, so that is why the boron becomes more electron deficient. But here in this case there is methyl group which is electron donating, means electron density is moving towards boron. So that is why the electron attracting power of boron becomes weaker, and that is why it is a weak base. So here the reactions of methylamines shows that the strength of the base is also measured in terms of the enthalpy value, enthalpy change, and on that basis we can also determine the order of the strength of the base or order of the strength of the acid. For example, if we consider here the various amines, if we consider the amines, that is bases, then if we place here the values of delta H for H plus addition in kilojoules per mole, and here if we place the pKb values, then we can also have here delta H for product formation. Using here BF3, that is order of BF3 as a Lewis acid, then BME3, that delta H kilojoules per mole, and tertiary B, tertiary butyl thrice, that is order. Then we will get the values like this. So if we find here NH3 is a base, NH3, then delta H values are minus 846 kilojoules. pKb in aqueous solution are like this, 4.75. NH3 with this BF3 has order 4. With BMNE3, the change in enthalpy delta H is minus 57.53, and order with this tertiary butyl boron is second order. Then if we see the next base, that is CH3 NH2, then the values are like this: minus 884, 3.38. Here it is second order. Here it is minus 73.81, and this is first order. Then for CH3 twice NH means Me to NH is minus 912, 3.23. First order means it is minus 80.58, and it is order 3. Then CH3 thrice N, CH3 thrice N, it is minus 929. It is third, 4.20. It is 3 minus 73.724. Then other amines are like this: tris C2H5 thrice N, then quinipyridine, it is, and pyridine, last is pyridine. So CH3 thrice, C2H5 thrice N has the values minus 958. Here it is 967. Pyridine has minus 912. Here the values are about minus 42, minus 84, minus 84, and minus 74.9. So these values are obtained, means explaining about the strength of the base and strength of the acid with respect to each other. If we consider the unsubstituted amine, that is ammonia, that is NH3, it has delta H for H plus is minus 84.6 and pKb is 4.76. So if we compare, the H plus is smaller in this acid, and this can easily form the adduct, so it can easily give NH4 plus ion. With this substituted, alkyl substituted amine, that is CH3NH2, the delta H for this H plus addition is more, that is CH884. So this is because their CH3 is electron donating, that is inductive effect, and that is why this nitrogen, means electron pair on nitrogen, can be strongly donated to this H plus. Then again in case of Me3N or this Me2NH, you find that these values are increasing, means the strength of the base increases in this direction. Again, if we come here to this triethylamine, the value is again increasing. So compared to Me, the ethyl group is more electron donating, and there are 3 such electron donating groups to be attached to this nitrogen. Therefore, strength of this triethylamine is more when acid is H plus, and quinolidine is also strongly basic. So it has structure like this. So we can have the benzene like structure here and still like this. So the quinolidine is having structure like this. So here the alkyl groups are pinned, means these are attached here. These two groups are attached to here, pinned. That is why their steric effect is minimized. They are not more interfering, and that is why it is becoming a more or stronger base. Here it is nitrogen. So the strength of the quinolidine is more, and it has value 967. Pyridine is also having the value 900 minus 912. So it is also a strong base. Now if these bases are compared with these BF3 acid strength, the acid strength is like this. So within these four bases, the order is like this. The strongest base for BF3 is this Me2NH. Then next is MENH2. Then next is Me3N. Then ammonia. And the BME3 has values like this. So these values are increasing here. It is more. So it is supporting these values. You will find here that these values are supporting here. So for this order 1, 2, 3, 4. And in case of this tertiary methylboron, the order is like this. So here NH2 is stronger base, then NH3 is stronger. Here this order is not like this, because here tertiary butyl group is attached to boron. Means boron is attached to 3 such tertiary butyl groups, and that is why the steric effect is enhanced here. So in case of NH3, the steric effect is less, and again in case of this, the steric effect is less, because the here methyl group is also a donor, electron donor. But as these methyl groups are increasing, the number of methyl groups are increasing, the crowding takes place, and this shows the steric effect, which decreases the order of these tertiary butyl, means tris tertiary butyl boron as acid. So here quinolidine is the case of this back strain. Here these methyl groups, means CH2 groups here are pinned here, and that is why the strain is called back strain. So with this we will stop our discussion. So thanks for watching this video. If not, please subscribe to this channel. We will now bring more videos for the benefit of graduate students of chemistry, as well as postgraduate students of chemistry, as well as the students of MPSC and UPSC. So you will be benefited definitely. Please push the like button and support your favor. So thank you very much. Again, now we will meet next time with new point.